So, with the canonical ensemble, we showed that we could describe the probability of the subsystem using this expression here, that the relevant partition function is described by Q, and that we could get the Helmholtz thermodynamic potential by using that partition function. Okay? Now the reason we went through all this trouble with the canonical ensemble is that it plays a central role in statistical mechanics, specifically the partition function. So the canonical partition function plays central role in StatMech. Okay? So for example, previously we looked at the microcanonical ensemble, and now we're dealing with the canonical ensemble, right? And they each have their own different partition functions. And what we could do is we could actually link the two together. So these two partition functions are related to one another. Okay? Because we know that entropy, we could relate it to the Helmholtz thermodynamic potential by this expression. And that if we plug in this into here, we get this. ln of Q, right? And so if we go through this derivative, we write it like this: KB ln of Q plus KB T over Q. And we know that Q is this. Or we could write it in terms of that. So let's do that. So that will give us J U sub J over KBT oh, there's another negative here. So those negatives will cancel. Okay? Alright. So we have exponential of negative U sub J KBT. Alright. So the first thing I'll point out is these T's will cancel. Okay? And then here, what we have, if we bring back the Q and put it underneath here, so if I link these two things together, okay, and we know that by definition it's P sub J, right? That's what we have up here. Okay, so we have entropy. We now have KB ln of Q plus KB summation of, let's see, KB, actually there should have been a square here. So we have KB U sub J over KBT P of J. Okay. Now, one thing we could do is we're just going to play a little mathematical trick here. KB ln of Q. Then we're going to have the summation of P of J. And we're allowed to do that because we know here P of j is just 1, right? So we're actually not affecting the value of this term at all, right? So we're just adding summation of P of j there plus the KB summation of j u sub j kbt P of j. Okay. You know, I'm keeping these around because I'm going to combine them now in this next step. KB, whoops. And so we have summations of P of j on both sides here. So I could factor that out now. ln of q plus u of j kbt. Okay. And really, this u of j kbt, if I factor out a negative sign, I could rewrite it as negative ln of the exponential negative uj kbt. Right. And the reason for doing that is because it allows me to then rewrite this entire expression like this. Since I factor out a negative from the entire thing, that would make this negative ln of q. And so then playing around with the log rules, we get this. Divided by q. Okay, and once again, we have this exponential over q. That, by definition, is P of j. So, in the end, we find that S is just equal to negative KB summation P of j ln of P of j. Right? And this we've seen before. This is the Shannon entropy equation. From Module 5.